Okay, so I'm going to finish the problem that we started today in class on Wednesday, September 2nd, okay, in our statics class, engineering science 2113, and we are looking at simplifying our force and moment system with a resultant force that's some distance away from our point C. So we did get the free body diagram drawn. If you weren't in class, um, cover up, just stop the video, draw your free body diagram, and make sure that you can draw the appropriate diagram. So now we need to start working on our forces. So I need to get my resultant force in the x direction. And I do that by summing forces in the x direction, and I'm going to call to the right as positive. So I'm just going to start at A and work my way around. So I'm coming up here, and I can see that I have a negative 500 newtons times cosine 60. Okay, I'm going to come around. That's a moment. It does not have units of just newtons, so I know to move forwards. And then I come around the corner, minus 4/5 times 250 newtons. So if I'm keeping up with units, it really is helpful to know what should be in my equation and what shouldn't. And I get negative 400 newtons, and I'm going to call that 450 newtons acting to the left because I like to see what's going on. Then we need to sum our forces in the y direction so that we can get a resultant force in the y direction. And again, I'm going to start at A, work my way around. So I have negative 500 newtons sine 60. I'm going to come around, minus 300 newtons, come around, minus 250 newtons times 3/5. And if I do my algebra correctly, I get negative 883 newtons. And again, I'm just going to show that that's 883 newtons down. Okay, so I need to figure out directionally which way that goes. And I like to just kind of start with my XY coordinate system. If I was at point C, that's where I'm looking at, point C, at C. And I can see that I'm going over 450 newtons. And then I'm coming down 883 newtons. So when I find this angle theta, I know that it's directionally coming into the third coordinate, or the third system over here. Okay, I also like to draw it kind of to scale so that I have a visual of what value that theta might be. And I can see we're about a 1 to 2. So I'm bigger than 45 degrees. Okay, and that way I can kind of check my numbers as I'm going through. So we have tan theta equals theta opposite, opposite over adjacent, equals 883 newtons divided by 450 newtons. And when I divide that out, I get 883, 450 divided by, I get 1.9622, and my units go away. So now I have tan theta equals 1.9622. So theta equals the inverse tangent of 1.9622. So theta equals inverse tangent 63 degrees. And that makes sense with how my figure looks. So at this point, if I'm looking back over here at point C, then I have resolved my forces. And my forces can now be shown here at C coming down, okay, at 63 degrees. And how do I find the magnitude? So now we use Pythagorean theorem that resultant force is the square root of my x component squared plus my y component squared. So I have the square root of negative 450 newtons squared plus negative 883 newtons squared. Okay, and let's figure out what that is. So I have 450, I have 450 squared. That's not 450, is it? 450 squared. And then I have 883 squared. Add them, square root. So I get a value of 991 newtons. Okay, so if I wanted to come back up here, this is at 991 newtons. Now all of these forces, I've gotten rid of the x and y components, but all of these forces are also causing a moment about point C. So that's my next step. Okay, let's come down here. So let's sum our moments. And specifically, we are going to go about point C. We want to see what the effect is on point C. And we are going to use right-hand rule, counterclockwise positive. So let's start here at A. This y component, if I see it runs along this vector line, it's a y component, so I need to look at an x distance. So I can put my pin on the x-axis that runs through C. If I were to push down, I can see that I do indeed have rotation, and it's rotating clockwise, so it will be negative. So I have negative 500 newtons times sine 60, and now I need that perpendicular distance. So I need the distance that goes from, okay, this axis coming back, and that is going to be 1 meter. Up the axis, perpendicular back, 1 meter. Okay, now let's look at this component. It's running in the x direction, perpendicular distance goes up. So I'm going to put my pin through the y, okay, through the y of point C, and I'm going to push my pin to the left, follow that vector line. And I can see, yep, I do have rotation. It is clockwise, so it is negative. So I have minus 500 newtons cosine 60, okay, and its vertical distance is, I don't know how I wrote a 3 there when I can clearly see it's 2, so correct that. I have 2 meters. Okay. I have an applied moment at C. It is counterclockwise, so plus 400 newton meters. I have this 300 newtons. It is running in the x direction, so I need to look at a y distance. So let's put our pin. If I push down on my clock handle, I can see, yep, rotation occurs. It is clockwise, so it is negative. So I have a negative 300 newtons times 3 meters. And we're going to keep walking around our system, and you should find that we have the y component over here. Okay. If this is my clock handle again, pushing down, it's causing rotation that is negative rotation. So I have negative 250 newtons times 3/5, and its perpendicular distance is 6 meters. So I have a negative 500 cosine 60, 1 meter. I have units of force distance, minus 500 times 2 meters. That is again force distance. I have a moment that's applied, force distance, force distance, force distance. So I have everything unit-wise that's matching what the units on my moment should be. When I add this up, I get negative 2,333 Newton meters. And again, let's just see, what does that negative mean? Well, I'm using right-hand rule. So that means I am twisting counterclockwise. When I come back to my picture, I can get rid of all of this and replace it with a force at C and a rotation. But I want to figure out where the line of action of this, okay, force vector intersects, measured from C along the CD axis. So I need to figure out, do I move this force vector that's pulling down and to the left? Do I move it to the left of C? If I move it to the left, I can see that's going to cause clockwise rotation. If I move it to the right of C, I can see that's going to cause counterclockwise rotation. So I'm going to have to move it to the left to recreate this moment. So if our moment about C is going to be a force times distance, and we are moving in the x direction, that tells me it is the y component. So if I come back here and look at my components, my y component is 883 newtons. So Here's C. I have 883 newtons. I have 450 newtons. I have a moment of 2,333 Newton meters, and I want to move away from C. Do I move it to the left? I don't know why I drew that backwards. Do I move it to the left so that I can continue that same rotation, or do I move it to the right? And we can see it is going to be the y component times that perpendicular dx that causes counterclockwise rotation because the x component is on that line. The distance is 0. So I have 2,333 Newton meters equals force y is 883 newtons times dx. When I divide this out, okay, when I divide this out, I'm going to get that dx equals 2.64 meters. And specifically, I have to move in the x direction to the right. So now, let's get another pen here. Let's get an orange pen. I can replace all of these forces with this force moment. And now I can actually move that resultant force over 2.64 meters, which is going to be about here. And I have this new line of action. And I can plug my force at 2.64 over, and I can have a resultant of 991 newtons at 63 degrees. And I can replace everything with just that force vector. Okay? So if you're having problems, please visit with our TAs.